So let's think about what conditions apply as we move from region 1 into region 2. So that's really, in a sense, a third region, a so-called transition region, if you want. So let me think about this. So if you want, this is sort of a region 3, if you will. But it's kind of a special kind of, mathematical kind of consideration for this region. So let's kind of draw what's going on in this region. Here's function of x. I'm drawing for you the potential v of x. And the point is that this is this transition region as I go from region 1 to region 2. Now, from the outside, we're thinking of this as a discontinuous step in the potential. But what we know physically is that that step in the potential really corresponds to, at some scale, a smooth potential function that would look like this and is just curved over very, very quickly, going from one value to another. So this is what it might look like. And that whole transition occurs in some tiny range between minus epsilon and plus epsilon. And the point is that ultimately we're going to be looking what happens when we make this epsilon some ridiculously small value, like something down on that Planck scale. And if that's my potential on that superfine scale, then my wave function will have some behavior across this transition region, and that's what we are going to be investigating. We are actually about to discover that the wave function is actually fairly smooth as it goes across this region. So I will just sketch some generic kind of wave function behavior across that region. I'm not necessarily making any claims about the behavior of my wave function. I just want to, put something on my sketch. We will prove our claims momentarily. So we're going to be thinking about this transition region. But the philosophy, remember, is to realize that I'm going to assume that my potential here is a smooth function, right? Down at some ultimate scale, I can always draw it as smooth, even sub-Planck scale, because the details at that subscale can't affect my overall physics. So, if I've got a smooth function like that, that takes us to an important result from the theory of differential equations. So, from the theory of differential equations, we can prove the following result. It comes ultimately through an argument that exploits the existence and uniqueness theorem. But if I have a differential equation that looks something like this, right, where I've got my function that I'm trying to solve for, right, as a times x, right, phi of x, and it's multiplying some function a naught of x, and then I've added to that some other function a1 of x times the first derivative of phi with respect to x, so d phi dx, plus then some other function times the second, which I'll call a2, times the second derivative of my function, plus etc. up to some finite order an times the nth derivative of my function, right? And if I have a differential equation where all of that equals 0, and just to emphasize why I'm bringing this up, if I have an equation of this form, I want you to notice, well, that is precisely the form of the time-independent Schrodinger equation, right? It's got some function times phi. It turns out there's no function, or a zero function, multiplying the first derivative of phi, and then I've got my second derivative times a function which happens to be 1, right? So I'm definitely talking about functions that have this particular form. And the statement I'm about to make is even more general than this, but I'm just applying it to this specific case. If I've got a differential equation of this form, which we do have, and this is important, the an of x are all what we would call smooth functions. And remember, our assumption is that yes, indeed, right, all physical functions down at some suitably small scale are smooth. Our question really is asking about ultimately how the wave function compares on one side of the transition to the other. But everything, at least this potential here, is smooth in here, and we're trying to see what that would do to our wave function. So if all of these an of x are smooth functions, and I want to give a mathematical precise meaning to that, what I mean is that these are infinitely differentiable So what I'm saying is that the function itself, right, phi, has a first derivative, and that first derivative has a second derivative, which is finite and well defined. And if it has a second derivative, that means the first derivative was continuous. And these all the way down to infinity, all the derivatives exist. So something mathematically that's infinitely differentiable. In math notation, they call those functions C infinity, which just means the derivatives up to infinite order are all in fact continuous. And if I have a differential equation that defines a function phi that's in this form with infinitely differentiable parameter functions like so, then I have a theorem which says that the resulting solution phi of x, right, is also smooth. By which again, of course, I mean infinitely differentiable. So that's very handy. So once we go down to a scale where our potentials are smooth functions, that tells us that we're guaranteed that our wave functions also will be smooth functions. And now that they are smooth functions, I can do some mathematics now to determine how my wave function on this side of the transition might or might not compare well to my wave function on the other side of the transition. So let's now let's make some use of this. So what does this tell me? Well, let's first think about the first derivative of my function, right? So let's see how the first derivative might behave. So let's consider, in fact, how the first derivative of my wave function on one side of the transition region compares, so we'll look at the difference, from its value on the other side of the transition region. And let's see whether or not this might be, for instance, 0 in the limit as I shrink the transition region down to 0, which would tell me then that the slope of my wave function on one side of this transition must match the slope of my wave function on the other side of that transition. Now, to see whether or not that may or may not be true, we can now use some math, because this function and all of its derivatives on this scale where now we are doing our analysis, they all exist. So I can use, for instance, the mean value theorem. The mean value theorem tells me the following. Okay, well, first, the difference in my first derivative, considering that everything exists, is the integral of my second derivative integrated from one point to the other, right? That's simple. Integral of second derivative is first derivative, and then I put in my two limits, and that gives me my right-hand side. But what's really nice, because not only do I know this function exists, I know it is a continuous function, which tells me then that the value of this integral by something known as the mean value theorem, you guys might remember the integral mean value theorem, you learn in your first calculus class, and here we see it's actually useful, tells me that this integral will equal the value of my integrand at some mystery location, phi x, where the mystery location is somewhere in my range of integration. So I'll call that x star. This has to be somewhere in my range, times then the range over which I perform my integral, which is 2 times epsilon. Now, we can make some progress with this because I actually know something about my second derivative. It is completely controlled by my Schrodinger equation. I, in fact, have that second derivative written down for us right up here. So let's copy the second derivative down. Right? So we know the second derivative here is going to be minus 2m over h bar squared times then, right, the energy minus the potential, but I'm evaluating this at my mystery point, x star, so it's the potential at x star, right, times then my wave function at that location. That gives me the second derivative of my wave function, like so, and that all is multiplying 2 times epsilon. Now, here is the cool thing. If I look at this quantity, right, if v of x is bounded, and by bounded I mean as I take the limit that this epsilon here goes to 0 and shrink this to a super sharp point, while I'm taking that limit, I'm the potential, notice, always stays between V, right? I mean, between 0 and V naught. It's not suddenly becoming infinite or anything, right? So as long as I have a potential that is everywhere finite and stays everywhere finite as I shrink this boundary down to 0. So notice, I'm not talking about, say, a delta function, which as I shrink my epsilon range, the potential goes to infinity. I'm speaking about a finite potential right now. So as long as Vx is bounded, right, this term is finite, finite, right? Which means then that when I multiply it by 2 times epsilon, as I shrink this boundary down to 0 and make this effectively a discontinuity, this final result then will approach 0. So even if the step has a discontinuity at some superfine scale that we're not considering, we still find that the slope on one side of the boundary actually approaches the value of the slope on the other side of the boundary. So therefore, I can conclude that this function phi of x is continuous across the boundary, by which specifically I mean the value of phi on one side of my phi prime on one side of my boundary, say at 0 minus, it's really at negative epsilon, but it's the same idea, equals the slope of my wave function slightly to the right of my point at, say, 0 plus. Great. And if the first derivative of my function is continuous, what does that then tell me about my function? Right. If the first derivative is continuous, then that actually tells me that the function itself is continuous. So I have a second boundary condition, which says the actual value of the wave function a little bit to the left of the transition region must actually match, in the limit that I make that very, very narrow, the value of my wave function just to the right. Now, if you wanted to be a little bit more mathematical to prove this, you can use the same mean value theorem approach. You could subtract the value of your wave function on either side of the boundary. You can relate that to the integral of the first derivative across your transition region, which then by mean value theorem just evaluates that first derivative at some mystery point inside your region times the width of your region. But because this phi prime isn't doing anything unusual, it's actually keeping almost the same value, it's continuous, that then says that this difference also would approach 0. So you could prove it that way if you really cared to. The bottom line lesson here now, though, is a very important boundary condition. So this is boundary condition type number 2, which is that our wave functions phi of x and phi prime of x are always continuous across transition regions, across transitions. So that then allows me to link what is going on in region 2, which I pretty much have a complete handle on, to what's going on in region 1, where I have to begin to learn about what is happening. So we've got now these generic transition boundary conditions. The next thing that would make sense would be now to let's apply this in our particular case. So let's see how we would apply this for us. So we have 2 boundary conditions that I would apply. We are saying that phi at a location on either side of my transition region, which happens to be at 0, has to equal itself, right? This is BC number 1, right? Or boundary condition 1. This was the first of our boundary conditions, or let's just call this number 1 here, right? Now, phi, my function when I'm to the left of phi 0, that is actually the function I'm calling phi 1, and I need to evaluate it right before the transition, right? So I'm going to be evaluating phi 1 here. Where is my potential? It's way up here. So I want to know phi 1 just at the beginning of that transition region, which is effectively at x equals 0. So I need to put in here the value of phi 1 just to the left, and that better match phi 2 then, which is the function just to the right. And now phi 1 itself, I had a generic form for, right? I had a general solution, a1 cosine plus b1 sine, or I have form number 2. But I really like form number 1 here because I'm going to be putting 0 in for x. And then when I take the sine of 0, this term will just drop out. So I really like form 1 for these types of matching conditions. So we'll go with that then. So form 1 says I have a1 times cosine of k1 times x, but x in this case is basically 0, just to the left of 0, right? Plus then b1 times the sine of k1 times what is essentially 0 on side 1. That has to equal my function on side 2, which we already decided only had the term c2, times then e to the minus alpha 2 times x. X in this case is basically 0, just a 0 positive number. And now we can evaluate. As we had just said, as x goes to 0, sine of k1x just gives me 0, so this whole term goes away and gives me 0. Cosine of 0 just gives me 1. See how convenient the sine and cosine form is? So basically I just have a1 on the left-hand side. On the right-hand side, e to the 0 also just gives me 1. So I very quickly can conclude and tidy this up that a1 must equal c2. That's my first condition joining across that transition region. Now the second condition is that the derivatives must match across regions. So phi prime just to the left and just to the right must match up. And of course, if I'm just to the left, I'm really talking about phi 1. And if I'm just to the right, I'm really talking about phi 2. I can now take the derivative of phi 1. It's written down here, although I didn't write the x's, but we can imagine these are x's and then take the derivative and evaluate at 0. So when I take the derivative of a1 times cosine of k1x, that pulls out a minus sign. It pulls out the k1. There's the a1. And then the cosine of kx turns into sine of k1x. But x, remember, I'm evaluating at 0. So times 0 minus. Then I have to take the derivative of the second piece. The derivative of the second piece would be derivative of sine of kx. We'll pull out a k, so there'll be a k1, b1. The sine becomes cosine, and then k1 times. Now, x is going to be evaluated at 0, so times 0 minus. And that then must equal the derivative of my right-hand side. So when I take the derivative of c2 e to the minus alpha 2x, it just pulls out a minus alpha 2. So there'll be a minus alpha 2, c2, and then my exponential is again e to the minus alpha 2, and we're evaluating just to the right of 0. Whew. Okay, we're on a roll now. I think we can see sine of 0 here just gives me 0. That term goes away. Cosine, again, the sines and cosines work so nicely. That just gives me a 1, very simple. And on this side, the exponential also conveniently just gives me a 1. So I have a very simple relation that k1b1 equals minus alpha 2c2. So I can now actually solve these two equations. Let's just write it down to be a little more tidy. So I just learned that k1b1 is minus alpha 2c2. That would give me my second equation. We can then solve these for our unknowns. So let's see here. I guess I just learned that c2 will equal minus k1 over alpha 2. I'm focused on this equation up here times b1. And then I also knew from up above that a1 and c2 were the same thing. So this will give me a1. So now I know a and c both in terms of b. So that gives me then all of the constants in here. And so I can finally write down the solution to the time-independent Schrodinger equation as one overall function. And then armed with this function, we can begin to think about the physics of what will happen in my collision. So this function I can write down. It's got two branches, right? When x is less than 0, I'm talking about phi 1. And phi 1, you remember, where was he? He was way up here, right? It's just a1 times cosine plus b1 times sine. So I think I could do that. So A1 times cosine. So A1 has this value. So there's going to be minus K1 over alpha 2 times B1. That's A1. And A1 multiplies cosine of K1x. Plus then I had B1 times the sine function. B1 times sine of K1x. And all that is phi 1. So that all applies, K1x. That all applies when x is less than 0. The alternative locations are x greater than 0. And by the way, at x equals 0, the wave function is continuous, so you can choose either of these two for the equal value. Maybe we pick this one. And now that side, the phi 2 side, was just C2 times my times my decaying exponential, and C2 again has this particular value, minus K1 over alpha 2, and that then is multiplying B1 to give me my C2, and it's my C2 that's multiplying my decaying exponential, e to the minus alpha 2x. So now that gives us then our final solution to the time-independent Schrodinger equation. You will notice there's a factor of B1 that we could factor out of everything. That just sets my overall normalization. So let's make a sketch of this, though. It'd be very good to see what this kind of thing is going to look like. So here's my sketch. Here will be, I'm plotting phi of x versus x to try to understand how this behaves. So when x is positive, right, I just have this decaying exponential behavior. Let's just pretend for the sake of argument that B1 is a positive number so we can track our signs. So that means this thing is going to be a negative decaying exponential for x greater than 0. So it would look something like this. It would start at some negative value and then be decaying exponentially, like so. Might look like that. Now, if we want to make a sketch of this type of thing, we want to be careful in our sketches, right? Actually, I want to make this here a little steeper, so let me make them a little more steep, decaying exponential. Right, that's its value here. You want to be a little careful at locations where you join your solutions together, right? We have a theorem that tells us that whatever the wave function is doing on this side, which is just these sines and cosines, but whatever it's doing on this side, it has to join up continuously and hit this point at x equals 0. But it also has to match the slope. So I find it very useful actually to sketch the tangent line in here, right? And that then tells me what the function has to look like on this other side of the boundary. And then on this side, it has to continue with this value and this initial slope. But then we know it looks like some kind of sines and cosines. So it will have to look something maybe like so, right? I'd have a sketch that would then look something like this. And the last comment I'd like to make here is that in region 1, right, you notice we have this kind of wave behavior. In wave physics, this is usually what's called a standing wave, is what we have here in region 1. And in region 2, we have this exponentially decaying region. This is frequently what's called an evanescent wave type behavior, where we have the decaying exponential. Notice here in the allowed region, I'm always curving toward the axis, whereas here in the forbidden region, notice I'm always curving, I have downward curvature. I'm curving away from the axis, but it's perfectly balanced, so I never go diverging towards infinity. It has to respect that boundary condition very, very far away. So this is the generic behavior I could expect to find in region